Ladies and gentlemen, it is our great pleasure to present our recent study on the development of dynamic fracture in a solid with multiple cracks at the first virtual European Conference on Fracture. We are Koji Uenishi, Yuki Fukuda, and Kunihiro Nagasawa from the University of Tokyo, Japan. Here is the outline of our presentation. First, the background behind this research theme is introduced. Then, the objectives of the study will be mentioned, and the results of laboratory and numerical investigations will be described. Finally, conclusions will be given. Let us briefly mention the background. For the enhancement of the integrity of structures consisting of brittle solid materials, it is essential to investigate mechanical destabilization due to fracture development in such brittle solids. Although the mechanical behavior of a single crack, or a source of further fracture under certain loading and environmental conditions, has been extensively studied, in reality, multiple cracks may exist, expand, and interact intermittently with each other in quasi-static and/or dynamic ways. However, the collective, global, behavior of such multiple cracks, as well as its connection with every individual, local, crack motion, has not been fully understood yet. Therefore, here, by using the experimental technique of dynamic photoelasticity in conjunction with a high-speed digital video camera, we examine fracture evolution in a two-dimensional, initially linear elastic rectangular polycarbonate specimen where sets of cracks are prepared by a digitally controlled laser cutter and tensile strain with a prescribed constant rate is externally applied. We trace local fracture development around each individual crack, and simultaneously, we obtain global stress-strain curves and physical properties like tensile strength of the specimens. As theoretically predicted by Gomez, Uenishi, and Ionescu in the journal Engineering Failure Analysis in 2020, the stress-strain relation is largely dependent on the prescribed strain rate, and, for instance, at least for relatively smaller strain rates, the global tensile strength increases with the strain rate. By knowing the above global characteristics, then, we concentrate our attention to more local, secondary fracture induced by the extending main or primary fracture and its influence on the global nature of the specimens with multiple cracks. For various different distribution patterns and values of density of initial cracks, we observe the dynamic evolution of the primary fracture and the fracture-induced waves, as well as the generation of the secondary fracture. Now let us briefly show you typical experimental results. As mentioned above, photoelastic polycarbonate specimens containing multiple cracks are prepared, and uniaxial tensile testing is performed under several different prescribed driving speeds or strain rates. Besides the global stress-strain relation, local dynamic stress evolution in the specimen is recorded by a high-speed digital video camera. The right figure illustrates an archetypal specimen used and elongated by the tensile testing machine. This picture shows the isochromatic fringe patterns or contours of the maximum in-plane shear stress dynamically developed in the specimen, just before the primary fracture is initiated, time 0. The driving speed in this case is 100 mm per minute and the following photographs are taken at a frame rate of 50,000 frames per second. Due to the action of the external load, the primary fracture develops. It moves from left to right. Also, branching of the primary fracture can be observed in this experiment. Here, at time 80 microseconds, total split of the specimen by the primary fracture as well as the initiation of the secondary fracture, which will propagate to the opposite direction, can be identified. At time 140 microseconds, the propagation of the secondary fracture arrests. Surprisingly, this arrested secondary fracture will resume its propagation in 200 microseconds, although no additional external load is exerted to the specimen. Here and after, the resumption of the propagation of the secondary fracture can be recognized. At this point, let us summarize the experimental results. This diagram shows the relation between the nominal stress and the nominal strain experimentally obtained for 3 different driving strain rates. As predicted theoretically by Gomez, Uenishi, and Ionesco, a higher strain rate gives a higher tensile strength corresponding to the primary fracture. Dynamic fracture development can be categorized into 3 stages. The first stage is propagation of the primary fracture, between time 0 and 80 microseconds. The second one is initiation and arrest of propagation of the secondary fracture, between time 80 and 140 microseconds. The last one is resumption of propagation of the secondary fracture, between time 340 and 400 microseconds. Obviously, the secondary fracture propagates even without additional external load. That is, its expansion is owing to fracture-induced waves. Let us move to the numerical part of the study. Finite difference calculations have been performed. With the spatio-temporally second-order accuracy. With 361 times 1201 orthogonal grids. For a homogeneous, isotopic, and linear elastic material with mass density 1200 kg per cubic meter, shear modulus 820 MPa and Poisson's ratio 0.37. For visual clarity, here, dynamic stresses generated by the primary fracture are shown, with no secondary fracture included. As in the experimental photographs, contours of the maximum in-plane shear stress will be depicted. The primary fracture propagates at an experimentally observed speed of 563 meters per second from left to right. Around the tip of the primary fracture, so-called the rupture front wave develops. At this stage, regions of stress amplification can be identified at positions away from the primary fracture plane. At these amplified regions, the secondary fracture will be initiated. Upon total split of the specimen by the primary fracture, Rayleigh surface waves are generated and propagated upwards and downwards along the vertical free surface. The surface waves will move to the edges of the specimen, reflected and then diffracted to cause further fracture, or more exactly, the resumption of propagation of the arrested secondary fracture, at a later stage. The connection between the secondary, further fracture and the dynamic waves can be summarized as follows. Number 1. Generation of the rupture front waves around the tip of the primary fracture. Number 2. Initiation of the secondary fracture owing to the waves induced by the primary fracture. Number 3. Resumption of propagation of the secondary fracture by the reflected and diffracted Rayleigh surface waves. Here are our conclusions of the observations. We find that after a total split of the specimen into 2 by the propagation of the primary fracture, the secondary, delayed fracture is initiated and propagated at a remote distance from the primary fracture. That is, fracture propagation may jump in solids with multiple cracks even when no additional external load exists. Moreover, in our observations, the secondary fracture moves in the direction opposite to the primary one. Since the specimen is completely divided by the primary fracture, the external load applied quasi-statically by the tensile testing machine to the specimen until the total split becomes 0 before the secondary fracture starts. The secondary and further fractures, or a cluster of fractures, are obviously not caused by additional external energy, but by dynamic waves produced upon enlargement of the primary fracture in this case. the development of the secondary and further fractures in a specimen of finite size may be concealed in the global stress-strain relation but may rather appear in a global pattern of dynamic wave radiation such as doublet or a cluster of earthquakes, i.e. ruptures in the solid Earth. We thank you for your kind attention.